Hey everybody, I am back and I am going to finish out chapter 6 in this video. Like I said, this chapter is pretty short and more or less just serves as a prep chapter for the next couple of chapters. Alright, so, and again, I'm not going over everything, I'm just going over some of the high points here, some of the really important things that you'll need. We talked about some of the bookkeeping and the different types of reactions that you're going to see. Now we're going to transition to a little bit more of a review of some old stuff that you guys did back in Gen Chem, thermodynamics and kinetics. All right, so let's start talking about thermo. Okay, so as you guys hopefully remember, thermodynamics is going to be dealing with energy change within a certain process. Most often, the context that you're going to be looking at it in is within chemical reactions, right? You run a reaction, most likely the energy is going to change. All right, and there's a few different angles and aspects that we can look at. Again, I'm not going to explore everything, but I want to kind of jump right in with this equation. This is one that you guys have probably seen before. Let me make a better triangle, or excuse me, uppercase delta. Delta G equals delta H minus T delta S. All right, hopefully you guys recognize this equation. This is the good old Gibbs free energy equation. So delta G in this equation refers to basically the overall change in energy. All right, and this is dependent on a couple of different things. First of all, it's dependent on this, delta H. This is the change in enthalpy. A lot of people get enthalpy and delta G confused. They think they're the same thing. They're actually not the same thing. I'll explain that more in a second. T is going to be temperature, and so, yeah, this is dependent on temperature. And also we have this, delta S. This is going to be the change in entropy of a system, right? And what is entropy? Entropy is the state of disorder. All right. So a couple of things here. Mathematically, we can see that delta G and delta H basically are directly proportional, right? As you increase, as you get more positive in delta H, you get more positive in delta G, right? However, since you have a minus sign in front of the delta S, it's the opposite. As you get more positive delta S, in other words, as you increase the entropy, you get a lower delta G. Okay? And this leads to different energy states. Right? And you guys have probably heard of a couple of different terms before. All right? You probably have heard of the terms exothermic and endothermic. All right, these terms basically refer to, they basically describe the delta H, the change in enthalpy, right? If something's exothermic, it gives off heat, so we refer to it as having a negative delta H. If something's endothermic, you have to input heat into the system, it absorbs it, so it's going to have a positive delta H. Right? And you may be used to looking at energy diagrams and sort of looking at curves and describing something as exothermic or endothermic. But don't forget, enthalpy is not the same thing as free energy change, right? Free energy also depends on entropy. A lot of times, what you see with delta H will be the same thing that you see with delta G, right? So, for example, in a given system, if you have a negative delta H, frequently you will also have a negative delta G. But it's not guaranteed because your entropy also is a factor. Not as big of a factor, but still a factor. So, what we're going to focus on then, instead, is two other terms, which hopefully you've seen before, that are very similar. Exergonic and endergonic. And basically, it means the same thing as exothermic and endothermic, but It's in terms of the overall free energy change. In other words, it's in terms of delta G, not delta H, right? So if something's exergonic, overall the system loses energy, so it has a negative delta G. If it's endergonic, you have to put energy into the system, it absorbs it, so you're going to have a positive delta G. Okay? All right, and yeah, that's important to recognize because we're going to look at energy diagrams here in just a minute, and depending on whether something's an exergonic process or an endergonic process, the curve's going to look a little bit different. For practicality purposes, in real life, as you're sort of trying to get a reaction to proceed, this is also going to have a direct impact on how what we call spontaneous your reaction is. All right? You guys have probably heard this. You've heard of spontaneous reactions. These are reactions that will happen without an extra input of energy. In other words, if you mix up the reagents, they'll react without you having to heat it up or help it out or anything, right? Conversely, non-spontaneous reactions, you got to give some help. You got to infuse some energy in the form of heat, light, electricity, something else, right? As long as it's an energy source, right? Spontaneous reactions have negative delta Gs. Non-spontaneous reactions have positive delta Gs. All right? And we can represent this visually through energy diagrams. Yay, energy diagrams. I'm sure you guys have done these before. So this is just going to be a bit of review, but it's always fun looking at energy diagrams, so why not? All right. So I'm going to show you a classic example of an energy diagram. All right, so you have basically an XY plot. Energy's over here on a y-axis, right? And basically what you do is you draw a curve that sort of represents what's happening to the energy as you go through the course of the reaction, right? So here's one example of what one might look like. All right, and let's say we're doing this for just a very generic AB plus C minus yields BC plus A minus. All right. So at the very beginning, you have your reactants. AB and C minus. Okay. At the very end, you have your products. And in the middle, you have something called a transition state. This is sort of an in-between form that the reagents go through as they sort of progress from reactant to product. Okay? And this is a good example of a one-step reaction, right? We're going to see that one-step reactions have one transition state. What do you notice about the energy? Does it go down or go up as you go from reactants to products? Well, here's how you can look at it. All right, so let's draw a little dotted line here, sort of along the line of our reactants. A little dotted line here, corresponding to our products. The little gap in between is going to be our delta G. And you can see the line got lower, right? So this guy has overall a negative delta G. If your products are lower in energy than your reactants, then you have a negative delta G. This would therefore be an exergonic reaction, a one-step exergonic reaction. Okay? Now, let me erase this and draw another one. Now, sometimes you're going to have to add energy, right? So I can draw the same thing here, but I can make the curve look a little bit different. right? So you see here, again, we're kind of starting off with AB, C minus, BC, A minus. We have our transition state here. And now, again, we can look at our overall energy difference. And we can see that our delta G should be positive in this case, right? Our product had a higher energy level than our reactants did. This is a one-step reaction as well, but it is endergonic. All right. Very good. All right. Now, who says reactions only have to have one step, right? By the way, that has a name. If you have a one-step reaction, if everything that happens, all the mechanisms, all the electron movements, everything, if you have a one-step reaction, that's also referred to as a concerted mechanism, right? You can also have, I guess I'm underlining the wrong thing here. If I'm looking for like vocabulary words, I guess it'd be more that, right? Oh man, now I have to write it backwards again. You can have more than one step. If you have greater than or equal to 2 steps in a given reaction, sometimes not everything happens at once. You might have one electron movement in one step and another electron movement in another step. This is called a stepwise reaction. All right. So the two energy diagrams you just saw, those were for concerted mechanisms. One of them was exergonic concerted, one of them was endergonic concerted. Now, we're going to take a look at a couple of stepwise. And we're going to keep it pretty simple. We're just going to look at 2-step reactions. All right, so let's say we're kind of looking at that same goal, but maybe the reactants reacted a little bit differently. Let's say in this case, AB, before C minus actually did anything, AB sort of spontaneously, I don't want to use the term spontaneous, AB separated, let's just say that, into ions without any action of C plus. All right, so that happens separate from C plus. Excuse me, C minus. Then, and only then, once we form the ions, then the B plus can react with the C minus to make your final product, BC. Those are 2 distinct steps, right? So we have to account for this whenever we're drawing the energy diagram. All right, remember how in our one-step mechanisms we had one transition state? Well, since we have 2 different steps, that means we're going to have 2 transition states. So it might look something like this. Okay? So very similar, it just has one extra little transition state that we go to. Come on. There you go. So we'll call that one transition state 1, that one transition state 2. All right. Again, if you're trying to keep track of, what's what, over at the beginning, we just have a singular reactant, right? We have reactant AB. It goes through, it separates, and so that gives you A minus and B plus. All right, so this part right here, this is sort of the end of the first step and simultaneously the beginning of the second step. So at this point, we also introduce in our C minus, and at the end, we end up with our product. Okay. If you want to determine whether this is exergonic or endergonic, well, again, draw the little dotted lines that connect them, and you can see the delta G goes down, right? You get an overall lower energy after you finish making the product. So this is going to be an example of an exergonic. Sorry, kind of sloppy crossing over into the graph, but I'm running out of room. All right, so this is an example of a 2-step exergonic reaction. All right, well, just like last time, we can have, if we can have one-step endergonic reactions, why not two-step? And we can. So you could have something like this. Right? It's going to be basically the same, right? At the beginning you have A, B. Over here you have your first transition state. Over here you have your second transition state. Over here we have our products. And we introduce our second reactant. And over here we have our final product. Okay? And you can see here, the energy level of our product, BC, is higher than that of our reactant, AB. All right, since it's higher, this guy is going to be endergonic. All right, very good. Again, just from years and years of teaching this, I just want to instantly say, does that make sense? Does anybody have any questions? Because that's my thing. That's what I always say. I'm not hearing any questions, so I'm assuming you got it. Ha, ha, ha. In all seriousness, if you need to get further explanation, please let me know. Okay. So that's basically kind of an overview. And like I said, this is all a review. You guys have seen this before. That's basically a review of thermodynamics. All right. Now I want to talk about kinetics. How fast does a reaction go? And that's really what kinetics does. How fast does a reaction go? A lot of people get kinetics and thermo mixed up, right? So, for example, they think that the faster a reaction proceeds, they'll think it's more spontaneous. They actually have nothing to do with each other. A really good example of this is newspaper, right? Have any of you guys ever, had newspaper that's really old, that's been stored somewhere, especially maybe somewhere in the light, and you look at it after it's been, stored for like 10, 20, 30 years, what does it look like? It might look kind of brownish, kind of yellowish, kind of, crinkly, kind of maybe a little bit more brittle, right? That's because there is a spontaneous chemical reaction that's been happening to that paper. It has been combusting. That paper literally, over that course of time, has been continuously burning. It's been reacting with the oxygen in the air and ambient heat to slowly combust that paper. Now, that might surprise you because you think of burning paper, you think you're going to have a bunch of black ashes and stuff, right? Well, if you eventually waited long enough, you would get that, but it would be, well beyond your lifetime, right? Okay, sorry about that. This particular reaction is spontaneous, but it's not very fast. It's just very, very slow. All right? Well, what determines whether something goes fast or slow? Well, if we go back to our energy diagram, let's talk about the one thing we haven't mentioned yet. And that's this energy hump, right? The energy hump that is used to form our transition state. You'll notice that transition states are always going to produce the high points of energy, right? It takes more energy to get to transition states. And then once you get past a certain point, it becomes easier to get it to happen, and then the energy falls off. The gap in energy between your starting material and the top of your transition state is called, I'm sure you've heard this before, the EA, the energy of activation, also known as activation energy. The higher your energy of activation, the slower the reaction. All right? This is what controls it. This is the gatekeeper for how fast your reaction goes. Now, there's certain things you can do to overcome this energy of activation sometimes. You can heat it up, right? Adding heat can help the system get to and surpass the energy of activation needed to form the transition state and make it go a lot faster. You can a lot of times increase the concentration of one or more of the reagents. That'll help sometimes. We'll take a look at that in just a minute. Right? Sometimes there's nothing you can do about it. It just depends. As I mentioned just a second ago, one of the things that you can do sometimes is you can change the concentration of one or more of the reagents. That leads us into rate equations. And hopefully, I'm pretty sure you guys did rate equations back in Gen Chem, right? We're not going to go really far in depth into these. I'm just basically going to tell you how, what you need for our purposes as we go forward in chapters 7 and 8. All right. Here's what a typical rate equation looks like. It's rate equals K times the concentration of certain reactants. I don't know why I put a parentheses there. That should be a bracket. All right. K is a rate constant. Higher the rate constant, guess what happens to your rate? It increases. It goes faster. Right, they're directly proportional. Reactants, now it's not necessarily always every reactant because the concentration of every reactant doesn't necessarily affect the rate of reaction. Sometimes only certain ones do. So you only include reactants that are in what we call, I'm running out of room, the rate determining step. Okay. If it is a concerted reaction, that's usually going to involve more than one reactant. However, if you have a stepwise reaction, a lot of times it'll only involve one. Okay? Let me give you an example. Let me give you a couple of examples, and this is going to be directly applicable to what we do in chapters 7 and 8. In fact, I'll show you using a couple of reactions that we might see. All right? Let's say we had this. See, we're going to take bromoethane. We're going to react it with some OH minus, and we're going to form an alcohol, and then we have Br minus as a byproduct. All right, so let's say we want to write the rate equation for this. Well, we're always going to have rate equals K, so that's something you need to include. All right, so now you have to include the concentrations of any reactants that are involved in the rate determining step. All right, well, let me ask you this. Is this a concerted reaction or a stepwise reaction? Hopefully you're able to recognize that this is a concerted reaction, right? Everything happens at once. You end up breaking a carbon-Br bond. You also end up forming a carbon-oxygen bond. All this happens simultaneously, right? So you ask yourself, what reagents are involved in these simultaneous processes? Well, this guy is involved, and this guy is involved. So what you would do is you would write the concentration of bromoethane and also the concentration of OH minus. They're multiplied times each other. All right. Now, it's not completely this simple either because sometimes we can have, or not sometimes, always, we're going to have an exponent. I'll just put N and X there for examples, right? Depending on exactly how the concentrations change the rates will determine what the exponents will be. The simplest situation is when you can do this. Let's say when we did this that we did a couple of experiments. We did this reaction, we measured the rate, then we did it again. We held the concentration of bromoethane constant while we doubled the concentration of OH minus. All right. When we do this, we see that the reaction also doubles, right? So basically, just doubling this one reactant had a direct one-to-one relationship with the rate. Right? If that's the case, then your exponent is just simply 1. And, if you don't even have to draw it, if you just leave it blank, it's understood to be 1. All right? But I'm just drawing it there so you can see it. Same thing. If we held OH minus constant, let's say adding bromoethane, let's say we doubled it, and again it doubled the concentration, or doubled the reaction rate, then the exponent there would also be 1. Okay? Now, it's not always like this. Sometimes you can double the concentration of a reagent and it might cause the reaction rate to triple or quadruple, right? So, you can have exponents of 2, 3, 4. You can even have fractions as exponents. You can have, OH minus raised to the 3/2 power or whatever. Good news for you. We don't have to worry about those because every one of the reactions that we're going to see in chapters 7 and 8, they're going to be very, very simple. Right? They are going to have exponents of either 1 or 0. So that makes your life a little bit easier. Once we have this established, we can assign something called a rate order. All right? And a rate order is just simply determined by adding up the exponents. So in this case, our exponents are 1 and 1, so 1 plus 1 equals 2. So this would be referred to as a second order reaction. Okay? Very good. Now let's try it. Let's do something a little different. Let's try this guy. All right. So this is 2-methyl-2-bromo, 2-bromo-2-methylpropane. All right, so it can react as well, and we can also make an alcohol, or we can make another substance out of it, but it goes a little bit differently. Let's say we had this, and the first thing that it did was it happened to kick off, whoops, don't want to draw that. Crap, okay, I have to redraw it. It kicked off a Br minus, and it created a carbocation. And then in a separate step, it reacted with something. Let's say it reacts with something called the acetate ion. Oh, well, that looks terrible. Something like this. Okay? And it produced this as the product. All right? Now, this is a stepwise reaction, right? We have 2 steps. Remember, we only include the reactants that are involved in the rate determining step. This reaction has 2 steps. They do not go equally as fast. All right? I can tell you that this step right here, the top one, that is the slowest of the 2 steps. It is a lot harder to break a molecule apart and form a carbocation than it is for a carbocation to react with a negative charge. That part happens extremely quickly. So the top one is the slow step. Slowest steps are the rate determining steps. So when we write the rate equation, we only care about the reagents involved in the rate determining step. How many reagents are involved in that rate determining step? Hey, it's just 1. So we only care about the concentration of this guy. And you would see this, happen in real life. You could add acetate ion, you could just keep dumping more and more and more of it till the cows come home. It's never going to change the rate of reaction, right? But in this case, if you double the concentration of 2-bromo-2-methylpropane, the reaction rate would also double. So it's just like last time we saw that was a 1-to-1. So the exponent there is 1. All right. So what's the rate order? Well, it's 1 plus nothing else. So the rate order, I can write this more efficiently. The rate order is 1, so it's a first order reaction. All right. pretty simple. And like I said, it does get a lot more complicated. You can have, third order, fourth order, fifth order, 4/3 order. You could have an infinite amount of possibilities. Hey, guess what? If you want to discuss that further, you can take a PChem class and study kinetics. But like I said, we're just interested in what we need to use to examine our nucleophilic substitutions in Chapter 7 and our eliminations in Chapter 8. Okay. There are zero order reactions as well. I'm not going to go over them because they're, again, not really within our, they're not really relevant to what we're going to be going over. But there are some reactions that, they don't change no matter how much you change the concentrations of reagents. So literally it's like 0 plus 0 equals 0 order. So, but that's neither here nor there. We're only concerned about first and second order reactions. All right, the last thing I want to mention is, and I'm sure you guys have heard this many times since high school, but I want to emphasize again. A lot of times we use catalysts in reactions. What do catalysts do? Hopefully you guys know. They increase the rate of reaction. They make reactions go faster. How do they do it? Well, they do something that will artificially lower that energy of activation. They lower that big energy spike, energy hill that you have to climb over. All right. We work with a lot of catalysts in organic chemistry. I've already mentioned some of them. A lot of acids can be used as catalysts, Lewis acids and Bronsted acids. Bases sometimes can be used as catalysts. We're going to see several examples of metal catalysts as we go through. Right. We'll see platinum and nickel, palladium, several examples of metal catalysts. Not so much in this course, but if and when you take biochemistry, you'll talk a lot about enzymes, which are biological catalysts. And you've probably talked about those quite a bit in your biology classes as well. They all work, though, basically the same way. They do something that will lower that energy of activation and make the reaction go faster. Okay, that is it for Chapter 6. Yeah, this is a really short chapter, like I told you. We're not going to have any homework from this. We're not going to have a quiz out of Chapter 6. Like I said, it's very much a prep chapter. Chapter 7 is where stuff gets real. This is where we start getting into reactions. So this is where the rubber meets the road. This is where we separate the adults from the not adults, I guess. I don't know. But this is where things can oftentimes get a little bit hairy. So make sure you're very proactive in keeping up with your studies and actively doing practice problems. That will especially be important once we start Chapter 7 and go beyond. All right? Okay, that's all I have for now. If you have any questions, let me know. Until then, I will see you next time. Bye-bye.